Mm. Okay, good morning to all of you. I hope that I am audible to all of you. Very warm good morning to all of you. So let us continue our session. So yesterday we have discussed the continuity and differentiability. So today I am planning to discuss the next, as a continuation, the application of derivatives. Okay. Before going to the application of derivatives, I would like to discuss the logarithmic differentiation. Actually, yesterday some of the students has asked in the morning session about logarithmic differentiation, natural logarithmic function, etc. So just I will discuss something about the logarithmic differentiation. After that, I will move on to the application of derivatives. Okay. So logarithmic differentiation is a very important part of this differentiation chapter. Actually, definitely we can expect some problem from that area. Okay, and many of the students are committing mistake there also. So the thing is, you should know all the properties of logarithm. That's all. Okay, for doing problems, you should know all the basic properties of the logarithm. Okay, there is no need of much knowing much about the logarithmic function. Okay, some property, the basic property you must know. So anyway, what is mean by a logarithmic function? A function defined by, for example, if I write f of x equal to 10 raised to x, f of x equal to 10 raised to x. Okay, this is called an exponential function. This is called an exponential function, and 10 is called here the base of the exponential function. Okay, so if I put different values for x, f of 1 means 10 power 1, f of 2 means 10 square. Like this, you will get different values for x, the function. Okay, I can put any real number. F of 0 means 10 power 0, that is 1. And f of negative 1 means 10 raised to negative 1, that is 1 by 10. Okay, so you can put any real number for x actually. Clear? Positive, negative, 0, okay, rational, or anything you can put actually. So this is called a exponential function. The base is 10 actually, and this exponential function we call the common exponential function. Okay, this is the common exponential function. The base is 10 actually. The base can be any real number which is greater than 1 actually. Okay, so I can define another exponential function, f of x equal to 2 raised to x also. F of x is 2 power x. Okay, 2 raised to x. So base is 2 here actually. The base is 2. Okay, so like that 3 power x, 4 power x, 10 power x, 100 power x, any number can be any real number which is greater than 1 can be the base of this exponential function. Clear? And when we take this function e raised to x, okay, e is also a real number actually. E is also a special real number, just like our pi. Okay, e has some importance, and this is not the time to discuss about the e, etc. And just you remember, just to understand, e is a mathematical constant, just like our pi. Okay, and the approximate value of e is 2.7 something actually. Okay, actually e is coming from a mathematical series actually, an infinite series, 1 by 1 factorial plus 1 by 1 plus 1 by 1 factorial plus 1 by 2 factorial plus 1 by 3 factorial, etc., etc., etc. Okay, this is actually the value of e. The value of e is coming from this series actually. Okay, this series is going to approach a number. Okay, it is converging to a number. Yeah, the limit of this value, where it converges, where it approaches, that value is actually called E. Okay, and that E is our E for the base for the exponential function. Okay, and this exponential function we call as the natural exponential function. So this E is coming from this series actually. Okay, if you calculate this value of E, you can find some approximate. Okay, if I take 4 places and you can calculate 1 plus 1 by 1 factorial means 2 actually. The 1 plus 1 is 2. Okay, if I take these two terms, the value is 2. And if I take this also, 1 by 2 factorial means 1 by 2 only. So you'll get 2.5. No? Again, if I take one more term, 1 by 3 factorial, 1 by 6. If I add one more term, 1 by 6, again you will get a value which is greater than 2.5. You know? Like that, you can keep on adding the terms, you will get the value of E. Okay, but it never, it is not possible to find the actual value of E. Okay. Anyway, it is greater than 2.7. Okay, less than 3. Very clearly, it is less than 3 also. So E is such a number actually, and that E is taken as the base of this our natural exponential function. Okay, so this is the function which is important for us. Whatever the function we are discussing in mathematics now, that is this E power x actually. Okay. So you just understand f of x equal to e raised to x, and it is called the natural exponential function. So here x can be any real number. You can put x equal to 0, you can put x equal to negative numbers, you can put x equal to positive number. Okay, everywhere you will get some output, some value for this function actually. So the domain is all the real numbers. Okay, this function, the domain is all real numbers. Now, can you guess the range of this function actually? What will be the range of this function? In the range, all the real numbers are coming or not? That's my question. In the range, all the real numbers are coming. Is it possible? All the real numbers can be in the range of this function? You think about that. You can put any value for x actually. Okay, x is the domain. X, the values which can be put for x is called actually the domain of the function. Okay, x can be any real number. Now the question is, what is the output when we put any real number for x? What is the corresponding output? Okay. Let me see if anybody is giving any answer in the chat box. Range is 0 to infinity. Okay. Open interval 0 to infinity. Okay. JNV Karaikal. Good. That's the correct answer actually. Okay. So the range contains only values from 0 to infinity. That is very clear. Whenever you put, whatever the value you put for x, e raised to x cannot be 0. Okay. E power x never 0. For any real number, e power x never 0, and e power x never negative also. You can put different values. If I put e power 0, put x equal to 0, the value is 1 only. E power 0 means 1. If I put some x equal to 2, e square is very clearly, it is a positive number. Square of a positive number means positive. If I put x equal to negative 1, e power negative 1, that is 1 by e. E power negative 1 means, e raised to negative 1 means 1 by e. No? 1 by e is a number, 1 by e is a positive number, because e is positive number means 1 by e is also a positive number. That means the range contains only real numbers 0 to infinity. Yeah, all real numbers greater than 0. Clear? Yeah. Then comes the exponential function. Sorry, logarithmic function. This is the natural exponential function. So definitely we can think about the reverse, isn't it? For example, if I write 100 is equal to 10 square. exponential form. Okay, 100 is equal to 10 square. Clear? Then in the reverse way, what we say is 2 is equal to logarithm of 100 to the base 10. Okay, so both are equivalent actually. Both are equivalent. 100 is 10 square. In the reverse way, we say that 2 is equal to logarithm of 100 to the base 10. Okay. In the same way, if f of x is e power x, suppose I take this as y, some y is equal to e raised to x form. Okay, y is equal to e raised to x. Then in the reverse way, what we can say, x is equal to, okay, x is equal to log of y to the base e. This value x is called logarithm of y to the base, to the base e. Okay, and that is called the natural logarithmic function, the reverse function, the inverse function actually. Okay, the inverse of the natural exponential function, that is called the natural logarithmic function. Okay, here the base is e, here the base is 10 actually. In this case, the base is e. When the base is 10, we call it as the common exponential function as well as common logarithmic function. When the base is e, we call it as natural exponential function as well as the natural logarithmic function. So, if I define f of x is equal to log x, it is understood that the base is always e only. Until and unless if we did not specify about anything here, it is understood that the base is e, and we will not write generally the e. Okay, we just write log x. So it is understood that the base is e only. Okay, so if f of x is defined as logarithm of x, then this function is called the natural logarithmic function. Okay, so if I take this as y, again in the exponential form, what we can write? This is same as e raised to y is equal to x. So both are equivalent. Okay, both are equivalent only. Log x equal to y implies e raised to y equal to x. Yeah, e raised to y equal to x implies log x equal to y. Both are inverses of each other. And what about the domain of the logarithmic function? Okay. So very easily you can now give the answer because it is the inverse of the exponential function. So it will be reversed, no? So what must be the domain of the logarithmic function? Because we know the range of the exponential function, that is 0 to infinity. So domain of the logarithmic function must be 0 to infinity, and range must be all real numbers. Okay, when we take the inverse, the domain and range will be interchanged. Now, we know if some function and its inverse operate each other. For example, in trigonometry, inverse trigonometry functions, you might have studied this one. Sine inverse of sine x equal to x. No? Sine inverse of sine x equal to x. Yeah, cos inverse of cos x equal to x. In the reverse way also. Sine of sine inverse x also equal to x. So when the inverse of a function and the function, the composition will be always the identity function actually. Okay, both will neutralize each other, like that we can think. The same idea, because we know e raised to x and logarithmic function, log x, both are inverses of each other, isn't it? So if I apply this idea, what we can write here, e raised to logarithm of x must be e raised to log x must be equal to, remember, e and log both are inverses of each other. Okay, The inverse of sine is sine inverse. We write sine inverse actually. The inverse of log is actually e. Inverse of e is actually log. So what will be e raised to log x? That's my question. It must be x only. Okay. E raised to log x must be equal to x. Just like sine inverse.
Yes. You can carry. Yeah. But just
Some voice is coming.
2 minutes back.
Okay, na? Realme
Fine, sir. Fine, sir.
Okay.
board.
Yes. Done.
Board. Okay. Okay, students, let's continue. In between, some disturbance is the, I think somebody is talking. Yeah.
2 minutes behind.
Okay. It's okay. So e raised to log x equal x. In the other way, what we can write? Log of e raised to x. Log of e raised to x. Reverse way. Okay, log first, e second. So log of e raised to x, that also must be equal to x only. Okay, because both are inverses of each other. So please remember, this will help you in problem solving. Okay, differentiation problem solving. So log of e raised to x equal x. Here x belongs to all the real numbers. Okay, x is any real number. E power x is defined for all real numbers. So please remember these very fundamental properties. Okay, sometimes we have to use these properties for doing problems. That's why I'm telling. Now there are some standard properties of this logarithm. Just I will very fundamental. Some properties are there. What about log 1? Log 1 for any base, log 1 is always equal to 0. Base e, whether it is base e, whether it is base 10, whether it is base 100, okay, the value is always equal to 0 only. Because if I take e also, base e means e power 0. E power 0 is 1 only. If I take the base 10 also, 10 power 0, 10 power 0 is 1 only. Okay, like that's why. So log of 1 is equal to 0. That's a very fundamental basic property. But we have to use sometimes all these things. Okay. And another property, log of a to the base a. I am telling very fundamental properties actually. Log of a to the base a. What must be here? It must be 1. Okay, because we know a power 1 is equal to a. A raised to 1 is equal to a. Remember the definition always. Okay, if log x equal to y to the base some base a, that means a raised to y is equal to x. Whenever a raised to y equal to x, we say that log x to the base a is equal to y. So log a to the base a must be 1 because a raised to 1 must is equal to a. So log of anything to the base, same base, will be always equal to 1. Okay. Log 10 to the base 10 is also equal to 1. Log 3 to the base 3 is also equal to 1. In particular, log e is equal to 1. Sometimes we will apply this, use this property. Log e is 1. There the base is understood. Okay, the base is e only. So log e to the base e is 1 actually. What we simply write, log e is equal to 1. Then comes the very important other properties. Logarithm of x into y, product of two functions, two terms. Logarithm of xy to any base. Okay, I'm not mentioning the base. Yeah, I can mention the base also, some a. Logarithm of xy is always equal to log x plus log y. Logarithm of x into y is equal to logarithm of x plus logarithm of y. All these are coming from the exponential properties actually, okay? These are coming from the exponential properties. Exponential property already you know. The basic properties a raised to m into a raised to n equal to a raised to m plus n. A raised to m divided by a raised to n equal to a raised to m minus n. That property is actually, okay? The proof is, if you want the proof very easily, we can prove actually. But it is not required for you in the examination point of view, I am telling, okay? But you can try by yourself. The proof is very simple. Suppose I take this value as some m and the second term as some n. Clear? Just I will give a rough proof, okay? Just log x is taken as m and log y take it as some n. Okay? Which implies a raised to m by definition of logarithm. Log x to the base a is m means a raised to m must be equal to x. Similarly, log y to the base a is equal to n implies a raised to n is equal to y. A raised to n equal to y. Okay. So if I multiply these two, actually I want xy, okay. I want xy actually. So multiply these two. So x into y equal to a raised to m into a raised to n. And we already know this a raised to m into a raised to n is equal to a raised to m plus n, isn't it? Very fundamental, property, exponential laws. So what we have got now, you see, something that is xy, okay? In the left side, you can see xy. This xy is equal to a raised to m plus n. Let us reverse back. This is the exponential form. So let it reversed in the logarithmic form. So this m plus n, m plus n equal to what? Log of xy. Log of xy to the base a must be equal to m plus n. Okay, we are applying the definition only. Okay, xy is a raised to m plus n. That implies m plus n equal to log of xy to the base a. Now what is m? M is nothing but log x to the base a, and n is nothing but log y to the base a. So how that is how this property is actually getting. Okay, so with this property is very useful for differentiation. So please remember the property. The proof is not required for the examination point of view. Okay, I'm just mentioning the proof for an idea. We can similarly other properties you can prove by yourself. Okay, just I will write the property only. The second, the next property, the number, whatever in continuation you can write. Okay, fifth one. The next property says that logarithm of x by y, logarithm of x by y to the base a, any base, okay, that is equal to log x minus log y. All these properties you may be knowing also, actually. Anyway, in another property, log of x raised to n, log of x to the power n is equal to n times log x to the base a. Okay, log of x raised to n to the base a equal to n into log of x. So log of x square means 2 log x. Okay, that's the meaning. Log of x cube means 3 log x. And another important property, this is also known as the base changing rule actually. Okay, log x to the base y, log x to the base y, this can be changed into another base actually, that is known as the base changing rule. This property I can write, yeah, I can express this in terms of some other base. Okay, log x to the base a divided by log y to the base a. So log x to the base y is equal to log x to the base a divided by log y to the base a. Okay, so base y is here, so here I have changed it both into base a form. All these properties are coming from the exponential properties, the basic exponential properties. Okay, just like the previous proof, you can do all the proof actually. This can be written in another way also. If I multiply here, so log x to the base a, log x to the base a, this term, log x to the base a is equal to what? Log x to the base y into log y to the base a. Log x to the base a is equal to log x to the base y into log y to the base a. Both are equivalent only. Okay. This property is known as base changing rule. Okay. Base changing rule of logarithm. So these properties, please remember, and these properties will help us in differentiation. Okay. In differentiation. I will just give an important means type of problem from usually asked from the differentiation part. Okay. If y is equal to x raised to x plus sin x raised to x. This is a very important type of question. Many times we can see in the question paper, etc. This kind of questions are asked actually. Okay. And students, many of the students commit mistakes also here. That's the problem. Many of the students commit some mistake here. So what is the mistake the students used to commit is, actually we cannot differentiate directly. Usually what we do, we take this x raised to x as some u, and the second term we take it as some v. Okay, u is equal to x raised to x, and v is equal to sin x raised to x. Then differentiate separately. Find du by dx by logarithm. Okay, and dv by dx, and add together. That's the method actually. Okay, if we find du by dx, dv by dx, then add together, that will give the answer. That is the correct method. But some students, what they do, they will do like this. Directly they will apply logarithm. Okay. Many of the students, they will simply apply log y is equal to log of x raised to x plus log of sin x raised to x. They simply write like this and do everything after this. The next stage they will write log of x raised to x means by property of logarithm log of x raised to x equal to x into log x, na? Plus log of sin x raised to x equal to x log sin x. Then they will do the differentiation everything and they will get the answer also. But it is totally wrong. Okay, totally wrong. From the beginning itself, we have committed a mistake actually. Okay, what's the mistake? This cannot be applied here. Okay, this cannot be done here. We cannot apply logarithm here because this is sum of two functions. Okay, we don't have a rule actually. There is no rule like that. There is no rule like this. Okay, log of x plus y. There is no rule. Log of x plus y is equal to log x plus log y. If it is there, okay. If there is some property like this, I can apply, and you can also apply here this in this way. But is there any property in this way? There is no property. Okay, so this is totally wrong only. Please remember, don't do this one. Okay, I am telling, don't do this one. Clear? This is totally wrong. You will not get any mark actually. Okay, so please take care of this stage. Okay, this step. So in order to overcome that problem, you can do this in another way. Using another way, the usual way, okay, you know, u and v taking separately u and v and applying logarithm. That is the usual procedure, okay? But I am telling this can be done in another way, okay? You know, this property what I have just told you, what is e raised to log x? You may be remembering. E raised to log x equal to okay, let me see any answer is coming or not. Yeah, x. Yeah, many responses are coming. It is x. Very good. Okay, so e raised to log x equal to x. E raised to log x equal to x. Clear? So this idea can be applied here. Okay, that means anything. This x I can express e raised to log x. Clear? So if some y is there, I can write e raised to log y. Okay, y can be written as e raised to log y. Or sin x, I can write it as e raised to log sin x. Clear? Anything. Sin x equal to e raised to log sin x. Okay. So this idea can be applied here. How we can apply here? So our function is like this. Y is equal to x raised to x plus sin x raised to x. Okay. So the first portion x raised to x. X raised to x actually. Okay. What I will write this as e raised to log of x raised to x. Anything I can write in this way. Na? Okay, x can be written as e raised to log x. That means x raised to x can be written as e raised to log of x raised to x. Okay, similarly, the second term also. The second term, sin x raised to x, that can be written as e raised to log of sin x raised to x. Okay, sin x raised to x can be written as e raised to log of sin x raised to x. Okay, now you see what happens. Okay, this is equal to e raised to log of x raised to x. By property, you know what is log of x raised to n? N log x. So log of x raised to x stands for x log x. E raised to x log x plus e raised to log of sin x raised to x. Log of sin x raised to x is same as e raised to x into log sin x. Property, same property. Log of x raised to n is n into log x. So log of sin x raised to x equal to x into log sin x. Okay. So if you rewrite in this way, there is no need of taking u and v in that method. Okay. Direct you can differentiate means no, you can directly differentiate. Okay. So our y is reduced, y has been reduced to in this way. Now we can differentiate as usual. What is dy by dx? Directly you can differentiate. Okay. Because derivative of e power something, you know. What is derivative of e? E raised to, for example, what is derivative of e raised to sin x? I am asking. What is derivative of e raised to sin x? Everybody can give the answer. Derivative of e raised to sin x. How to get it? We have to apply chain rule. No? There are two functions. One is e raised to x form. Derivative of e raised to x is e raised to x. Derivative of e raised to sin x is, first we have to write e raised to sin x. Okay, e raised to sin x, but not yet, not completed now. Into derivative of sin x, we have to multiply. Chain rule. Okay, into derivative of sin x. What is that? Cos x. Chain rule actually. Okay, so same thing here also. E raised to x log x. So first we have to write the derivative of e raised to x function. E raised to x function means derivative is what? E raised to x log x. Same thing. Now derivative of e raised to x is e raised to x. So derivative of e raised to x log x means first we have to write e raised to x log x into derivative of x log x is remaining. Okay, derivative of x log x. Chain rule, derivative of x log x. That can be easily written now. Product rule. Derivative of x log x. What is that? X into first function into derivative of log x means 1 by x plus log x into derivative of first means 1. Okay, product rule. X log x, product x into derivative of log x plus log x into derivative of x. That is over. First part is over. Now second, plus. Similarly, again, e power form. No? So derivative is the same itself. First we have tried the same as it is. Derivative e raised to log sin x into what we have to write? Derivative of x log sin x. Okay, derivative of x log sin x. Here again, product rule. Okay, x log sin x. X into log sin x. This is our function. X is the first function. Log sin x is the second function. Okay. So product rule. X into first function x into derivative of log sin x means chain rule. Log derivative means 1 by sin. 1 by sin x. And derivative of sin x means cos x. Okay. Derivative of log sin x means 1 by sin x into cos x. Okay. Plus log sin x into no, product rule. Log sin x into 1. Product rule. Okay. Clear? So derivative of e raised to x log x means e raised to x log x into derivative of x log x into derivative of x log x means product rule. X into 1 by x plus log x into 1 plus second term. Again, e raised to x log sin x into derivative of x log sin x. Derivative of x log sin x means product rule. X into 1 by sin x into cos x plus log sin x into 1. So differentiation is over. Differentiation is over. Okay, just you have to write the answer in a more simplified way. So that is equal to Again, you go back. E raised to x log x. Actually, what is that? E raised to x log x means that is nothing but x raised to x only. X raised to x, we have written e raised to log of x raised to x, and that is coming as e raised to x log x. So again, reverse it. Okay, this is same as x raised to x, the original term there. That is equal to x raised to x. Okay, this is x raised to x into, in bracket, you can simplify 1 plus log x, 1 plus log x, plus second part also, e raised to x log sin x. That is nothing but the original term, sin x raised to x. Sin x raised to x has been written as e raised to x log sin x. So again, we will write in the original form, sin x raised to x, in bracket, into x into cos x by sin x. That is x cot x. Cos x by sin x is cot x cot x plus log sin x. Okay. So this is our final derivative. Okay. If you want, you can do in this way. Otherwise, you can do in the our usual way. Take u, v separately, find du by dx, dv by dx, then add it together, you will get the same answer. Okay. But if you practice in this way, I think that this will become somewhat easier than the other method. Okay. It will save your time also. Okay. One more problem I will write. Cos x raised to sin x. Cos x raised to sin x plus log x raised to x. Find dy by dx. The question is find dy by dx. Okay. So in the previous method, you can also try. Okay. So this can be written as y is equal to what we have to write, e raised to log of cos x raised to sin x. E raised to log of cos x raised to sin x plus second term also e raised to log of log x raised to x. That is equal to e raised to what is log of cos x raised to sin x? You know the property of logarithm. That is equal to sin x into log cos x plus e raised to log of log x raised to x. Again, by the same property, that is equal to x into log of log x. Log of log x. Okay. Then differentiate. What is dy by dx? So derivative of e raised to something means the same itself. No? E raised to x means e raised to x. You can write as it is. No, ultimately, and you know that it is going back to the original function actually. No? Original function means cos x raised to x. So cos x raised to sin x. So you can now also you can write it. Anyway, the same function will come first. No? So that is same as the given term. That is cos x raised to sin x. So, cos x raised to sin x. I am writing directly here now, okay? Derivative of E power x is same as e power x. So cos x raised to sin x into, here we have to apply the product rule now, okay, into derivative of sin x log cos x. Derivative of sin x log cos x. So what is that? Product rule, okay? Sin x into derivative of log cos x means 1 by cos x into derivative of cos x means minus sin x. Product rule, okay? Sin x into derivative of log cos x. Derivative of log cos x means chain rule. 1 by cos x into minus sin x plus second function log cos x into derivative of sin x. Derivative of sin x means cos x. Okay. So the first part. This is the derivative of the first part. That is over. Plus the second part. Derivative of e raised to x log x. So you know, first we have to write as it is, whatever there. Okay. So e raised to x log x. That ultimately that is log x raised to x, the original term. Log x raised to x into derivative of x into log x. Derivative of x into log x. So product rule again. No? X into derivative of log x. Derivative of log x means 1 by log x. Derivative of the first logarithm. Log y means 1 by y, log x means 1 by x, like that. So log x means 1 by log x into derivative of log x. Chain rule, derivative of log x. That is 1 by x plus log x. Second term, second function is log x into derivative of x. That is 1 only. Okay. I hope that all of you must have got the answer also. So the differentiation is over. No. Differentiation is over. Now you just modify the answer. Okay. Just simplify the answer and write. So that's equal to the remaining thing everybody can do. Okay. Cos x is sin x into the x sin x into minus sin x divided by cos x. You can write minus in the beginning, minus sin x by cos x is tan x actually. So sin x tan x. Or you can write sin square x by cos x, doesn't matter. Plus log cos x into cos x. Log cos x into cos x. Better to write cos x into log cos x. The first part. Plus log x raised to x into log x raised to x into, in bracket you can see one x is x and 1 by x will cancel each other. So 1 by log x plus log x. Okay. So this is the final derivative. Okay. So you try, you keep on trying by taking examples of this type. Okay. Practice and make it perfect. So later it will be so easy for you. Okay. Within 2-3 steps, the whole answer will be ready. There is no need of taking separate u and v. That also you can do, no problem. But if you practice in this way, and the other part also can be, that mistake also can be avoided. No? Sometimes some people may directly apply logarithm as I have told in the beginning. Okay. So that also can be avoided if you apply this method this way. Okay. So that's about the logarithmic differentiation. Now I think it is clear. I can move on to the next topic, that is the application of derivatives. Okay. Is there any doubt you can put in the chat box? Okay. If any clarification is required. Okay, some responses are here in the chat box. Okay, now I could see. Very good. Is there any doubt you can put in the chat box now regarding the logarithmic differentiation? If there is any doubt or any clarification is required, so please put in the comment box. Now there is a question. Sir, how to prove anything power 0 is 1? No, sir. What is the value of log 1 to the base 1? Some comments, some responses are here. So how to prove anything power 0 is 1? Uh, what is the value of log 1 base to the base 1? I think uh, from school classes, I think we are studying this property x power 0 is equal to 1. No? That's, I think, very simple to prove actually. X power 0, the 0 can be, you can write some m minus m. No? X power 0, we can write x raised to m minus m. And exponential property says that x power m minus m is equal to x power m divided by x power m, and that is equal to 1. Okay, so very simple. You might have forgotten in the lower classes. You might have studied this actually. Okay, anyway, x power 0 is 1. That's another one question. Another question was, what is logarithm of 1 to the base 1? This is the question actually. Okay. Okay, good question actually. Log 1 to the base 1. So 1 square is 1, 1 cube is 1, 1 power 10 is 1. That's why this question has come, I think. Okay, but remember, in logarithm, the base is always greater than 1. Okay, whenever we define logarithm, the base value is always a real number greater than 1 only. We will never take the base which is less than or equal to 1 also. Okay, so there is no need of any explanation for this actually. We always take the logarithm, the base is greater than 1 only. Okay, we don't take the base as 1 actually. That is in the definition. Okay, clear? The problem is like this only, because 1 per 1 square is 1, 1 cube is also 1, 1 per 100 is 1. So in that way, if you think there may be a confusion actually, no? Okay, that's why the base is always greater than 1. Never we take the base as equal to 1 or less than 1. Okay. Another question is also there. 0 power 0. What is the value of 0 power 0? Okay, that's also a good question. Actually, these are not coming into this topic actually. Anyway, 0 power 0, 1 power infinity, infinity power 0, all these things we call it as indeterminate. Okay, 0 by 0, 1 infinity by infinity, 0 raised to infinity, like that. These terms generally we call as indeterminate. Okay. Okay. So shall we move on to the next topic? Okay, children. So now we will move on to the application of derivatives. Okay. So here in this chapter, uh, we have to study one application, that is rate of change. Rate of change. The next one is increasing, decreasing functions. Increasing, decreasing functions. And third one is maxima and minima. So these are the three topics which is included in the syllabus. Okay. Application of derivatives. In the earlier syllabus, there was much tangents and normals, approximations, all these things. Okay. Now in the present syllabus, only these are the three topics which is included in the chapter application of derivatives. It is also a very important chapter. Generally, there will be most probably a case study question from this area. Every question paper you can see a case study question paper. Yeah, some 5 marks question also maybe. Okay. So it's a very important chapter actually. Only the basic derivatives is required for this actually. The basic derivative idea. So first we will discuss about the rate of change. Okay. The first application, rate of change. So this is the very, very fundamental concept, yeah, idea of differentiation actually. Okay, whenever we write dy by dx, if y is a function in x, okay, we write dy by dx, yeah, f dash x. So what is measure actually? This dy by dx measure the rate of change of y with respect to x. Okay, how y is changing, at what rate y is changing when x is changing, yeah, with respect to x. Okay, so that is a very fundamental idea of the derivative actually. You know, the derivative actually begins from the velocity, you know. It starts from actually Isaac Newton. The two people are credited. The credit goes for two people actually, the calculus. One is Isaac Newton and other is Leibniz. Okay, Leibniz. Both people have developed this calculus at the same time, almost same time, independently. That's a interesting story actually. Anyway, so actually Isaac Newton has developed this calculus, yeah, fundamentals of calculus to in order to find the velocity, yeah, instantaneous velocity. Okay, you know, when the displacement is given, okay, for example, s equal to t square, a displacement is given in terms of time function, so time variable, s equal to t square, f of t is t square. So we know what is velocity. The velocity is nothing but a rate of change of displacement, you know? ds by dt. All these things you are familiar actually. So ds by dt stands for rate of change of displacement. Okay, rate of change of displacement. Okay, so fundamental idea of derivative is, and one idea is rate of change. Rate of change of s with respect to t. That is actually called the velocity. Okay. Now, in general, any function, y is a function of x. Okay. So dy by dx stands for rate of change of y with respect to the variable x. Okay. Suppose we have a variable circle. Okay, variable circle. Then the area of a circle, area of the circle at any instant is always pi r square. Variable circle means continuously the radius may be changing, increasing or decreasing. Then correspondingly, the area also will be changing continuously. Okay, increasing or decreasing. So there is a variable circle at any time, at any instant. The area is always pi r square. So this is a function. This area is a function of r actually. Okay, area is a function of r, radius actually. So if I write dA by dr, if I write dA by dr, you will get pi into derivative of r square means 2r. No? Pi into 2r, you will get 2 pi r. Okay. So this dA by dr represent what actually? This dA by dr represent rate of change of the area with respect to the radius. Okay, with respect to the radius. Imagine the circle is a means not a constant circle. Okay, it's a variable circle. Okay, just 1 minute. You can see in the screen, just like this. Okay, the radius is changing continuously. So the area, the circle area is also changing actually. Okay, at a different instant, the area, the value also displayed in the screen actually at a different positions. Different positions, the different area of the circles also displayed here. Okay, so I am telling about this kind of circle actually. Okay, you might have observed when we drop a stone or any object into a lake, a quiet lake, you know, when we drop a stone, then we can see that the circular waves are moving, just like this. What you have observed in the screen actually. Okay, the circular waves are forming. It is circular means circles continuously circle the increasing. The radius is increasing and area is also increasing. So imagine like that. Okay, so it's a variable circle, not a fixed circle actually. Okay, then dA by dr represent the rate of change of area with respect to the radius. Means how fast the area is changing. Okay, with respect to the radius. Suppose I want the rate of change at a particular instant. Okay, when the radius is 2. Okay, at the particular moment when the radius equal to, at that particular moment, what is the value of dA by dr? So I just put r equal to 2. So dA by dr is equal to 2 pi into the corresponding given value of radius is 2. That means I will get a 4 pi. 4 pi. Some unit may be there. Okay, if area, the radius is in centimeter, means the area will be 4 pi centimeter square per centimeter. Okay, in that particular instant, the rate of change will be 4 pi centimeter square per centimeter. Okay, so this kind of problems, it can be area, it can be volume. Okay, it can be surface area of a cone, surface area of a cylinder, surface area of a sphere. These are the basic mathematical objects, mathematical models, and this kind of problems may come here also. Okay, it can be volume, it can be surface area, it can be means area of circle, cuboid, like that. Okay, you only need the basic formula of area, volume, etc. That's all. That is enough for this topic actually. Okay, so this kind of problems actually we are discussing here. Okay, for example, let me take a question. Same problem, okay? The area of a variable circle is changing continuously. So what is the rate of change of its area when r is equal to 3 centimeter? Very simple problem what I have discussed just now. That's only, okay? The area, there is a circle whose area is changing continuously. The radius is changing continuously, so automatically area is also changing continuously. So what is the rate of change of the area at the instant when r is equal to 3 centimeter? So circle, there is a variable circle. Okay, the radius is r. Then area, let A be the area at any time. Then area of the circle at any time, it will be equal to pi r square. We have to start like that, okay? Let r be the radius and A be the area of the circle at any time, at any instant. Then area is always equal to pi r square. Then if you differentiate dA by dr, dA by dr is equal to pi into 2r, that is equal to 2 pi r. So this is the formula for the dA by dr. Now, if you want to get the dA by dr, so we have to find the dA by dr at the instant when r equal to 3. So put r is equal to 3 here, that's all. So dA by dr when r is equal to 3, that's equal to 2 pi into 3, that's equal to 6 pi. You know, 6 pi centimeter square per centimeter. Okay, it's a very simple problem actually. Now, sometimes the rate of change of the area and radius both can be given, okay, with respect to the time actually. The rate of change, the area is increasing at the rate of 3 centimeter per square per second. Yeah, the radius is increasing at the rate of 2 centimeter per second. Okay, so area and radius both can be given as a function of another third variable, say t, a time. Okay, at that time, how to do it? Again, the method is same only. Okay, suppose again the same problem, same type of problem. The rate of change of the radius, the rate of change of the radius of a variable circle, the rate of change of the radius of a variable circle is 3 centimeter per second. 3 centimeter per second. Then what is the rate of change of its area? What is the rate of change of its area when r is equal to 2 centimeter? Another question, okay? These are very simple questions I am taking in the beginning. The rate of change of the radius of a variable circle is 3 centimeter per second. Okay, the radius is changing at the rate of 3 centimeter per second. Then what is the rate of change of its area when r equal to 2 centimeter? Here also imagine this is a variable circle. The radius is continuously increasing or decreasing, changing. Okay, so correspondingly the area also will be changing. A rate of change of the radius is given as 3 centimeter per second. The radius is changing at the rate of 3 centimeter per second. Okay. So we have to find the rate of change of the area. So again, area of a circle. Okay. If you want, we can draw a figure like this. Remember, it is not a fixed circle, it is a variable circle. Okay. It is not a fixed circle, it is a variable circle. So at any instant, let A be the area and R be the radius. Any time, any instant at any time t, A be the area and R be the radius of the circle. Okay. Then as usual, we know that the area of the circle at any instant will be always pi r square. Then we write dA by dt. Okay. Here we have to differentiate with respect to the time. So dA by dt is equal to pi into the differentiation is with respect to t. Remember, okay, pi into derivative of r square with respect to t. Derivative of r square with respect to t. So that must be equal to 2r into dr by dt. Yesterday, I have explained why we are writing dr by dt, etc. Okay, now d by dx of y square. Remember, d by dx of y square is 2y into dy by dx. Okay, like that only. D by dt of r square, that is 2r into derivative of r with respect to t. We have to multiply. Okay, 2r into dr by dt. So, what is given in the question? The rate of change of the radius is given 3 centimeter per second. So, dr by dt is given. So, given that the rate of change of radius dr by dt is equal to 3, and we have to find the rate of change at the instant when the radius equal to 2 also. So, r is equal to 2. According to the question, dr by dt is 3 and r is equal to 2. So, just substitute it. Therefore, dA by dt is equal to 2 pi r, 2 pi into r means 2 into dr by dt is 3. So, what is the answer? 2 into 2, 4 into 3, 12. 12 pi centimeter square per second. Okay, 12 pi centimeter square per second. That means the area is changing at the rate of 12 pi centimeter square per second. It may be increasing or decreasing. Okay. If it is given increasing, means in the question, radius is increasing. So we have to take dr by dt as positive. Okay. And if it is given radius is decreasing at some rate, okay, decreasing, if it is given as decreasing, then we have to take the sign as negative. Okay, negative indicates decreases and positive increases. Positive indicates increases. That's all. Okay. Now let me take another problem. So please take this question. Okay. The volume of a spherical balloon is increasing at the rate of 25 centimeter cube per second. Find the rate of change of its surface area at the instant when its radius is 5 centimeter. I think the problem is clear to all of you. Please note it down, okay? The volume of a spherical balloon is increasing at the rate of 25 centimeter cube per second. Find the rate of change of its surface area at the instant when its radius is 5 centimeter. A balloon which is always spherical, okay? The balloon is also not a fixed balloon. It is a variable balloon, okay? The balloon, the volume is increasing at the rate of 25 centimeter cube per second. So what is the rate of change of its surface area at the instant when the radius is 5 centimeter? Okay. So here also there is a variable balloon. Suppose the radius is r at any instant. Okay. Let that we have to start. Let r be the radius, v be the volume, and surface area, yes, be the surface area of the variable balloon, variable spherical balloon, a variable balloon at any instant, okay? At any instant, the balloon is always spherical, okay? The volume may be increasing, but it is always spherical only. So R be the radius, V be the volume, and S be the surface area of the variable balloon at any time. Then only the thing we should know the basic formula, okay? So what is the volume of the balloon? Means sphere, everybody knows it is 4 by 3 pi r cube, okay? 4 by 3 pi r cube. So differentiate with respect to t. So dv by dt is equal to, everybody can write the derivative. There is no difficulty. It's very simple. 4 by 3 pi into 3 r square into dr by dt, isn't it? 4 by 3 pi. Derivative of r cube is again derivative of r cube with respect to t. D by dt of r cube, that is 3r square into dr by dt. You can a little modify, okay? 3 and 3 can be cancelled. So 4 pi r square into dr by dt. 4 pi r square into dr by dt. So this is dv by dt, okay? This is dv by dt. Now what is given in the question? You see what is given. dv by dt is given. That is 25. 25. So we will calculate what is the value of dr by dt? Okay. So given dv by dt, rate of change of the volume at that particular instant. Sorry, dv by dt is always same only. What is given? It is 25, no? 25. The numerical value only I am writing. 25 centimeter cube per second. Okay. So dv by dt is 25. And r is equal to, what is the value of r? That is given as 5. Okay. So if you substitute these values in equation 1, you will get 25 is equal to 4 pi into 5 square into dr by dt. Dr by dt is not given actually. So dr by dt, we are going to find out first. Okay. So all the known things, what are the given things, we have to substitute. So except dr by dt, everything we know, and you can calculate dr by dt from here. Okay. That is equal to 25. You can cancel directly. 5 square means 25 only. Okay. So that is dr by dt. Therefore, dr by dt is equal to, what is the value? 1 divided by 4 pi. Okay. 1 divided by 4 pi. Centimeter per second actually. Okay. Centimeter per second. So radius is increasing at the rate of 1 by 4 pi centimeter per second. Okay. But this is not our required answer. We have to find the surface rate of change of the surface area. No? Rate of change of its surface area. That is our target. For that, we should know what is the surface area formula. Okay. So what is the surface area formula? Yes, surface area of a sphere. Everybody will be knowing the formula. No? This fundamental formula. So surface area of the sphere is equal to 4 pi r square. Is it correct or not? Is it correct? Any comments? Okay. Some students have got the answer. Good. So let us find ds by dt. ds by dt is equal to 4 pi is a constant into the derivative of r square means 2r into dr by dt. Okay. So ds by dt is equal to 4 pi into 2r into dr by dt. Now we have to substitute. Okay. So this is equal to 4 pi into 2 into r, we know already given, r is given as 5 into dr by dt, that is 1 by 4 pi. Okay. We have to find the ds by dt at the instant when r is equal to 5. So r is already given, and dr by dt we already got 1 by 4 pi. So substitute both. In place of r, 5, in place of dr dt, 1 by 4 pi. If you calculate 4 pi cancels. Sorry, answer is 10. Okay. So it is 10 centimeter square per second. Surface area. No, surface area. So unit is square unit, centimeter square. That means the surface area is increasing at the rate of 10 centimeter square per second. Okay. Surface area is increasing at the rate of 10 centimeter square per second. Okay. So sometimes some problem may be asked from this area also for case study. Last year board examination, I think some questions in some question paper I have seen case based case study questions from this area also. Okay, so it is simple actually. If you know the basic formula, volume, surface area, all these things, all the basic models, okay, cylinder, square, sorry, circle, and cuboid, cone, like that. The basic formula, area, volume, that's all. Okay, if you know those formula, easily we can do it. Okay, let me take another question. Okay, this question. Find the points on the curve y equal x square at which the slope of the tangent is equal to the, sorry, this is a, okay, anyway, no problem. Okay, from this area only. Now I am thinking it is from some other part. Oh, no problem. Okay, so find the points on the curve y equal x square at which the slope of the tangent is equal to the y coordinate of that point. So note it down. Okay, so a curve is given y equal x square, and on that curve we have to find the points which satisfy this condition. The slope of the tangent is equal to the y coordinate at that point. So how to do it? So given curve is y is equal to x square. That's all. Okay. Given y is given curve is y is equal to x square. It's a parabola actually. Okay. Whatever it may be, y is equal to x square. So find a derivative dy by dx. So dy by dx equal to 2x. Everybody knows dy by dx equal to 2x. Now, what is the given condition? The slope of the tangent is equal to the y coordinate at that point. Slope of the tangent is equal to the y coordinate at that point. So we know what is the slope of the tangent actually. Geometrically, when we speak derivative, yesterday I have explained to you dy by dx stands for the slope of the tangent. Okay, dy by dx means that is equal to the slope of the tangent. So remember, slope of the tangent is equal to the y coordinate. That is given. Given that slope of the tangent is equal to the y coordinate. Slope of the tangent is equal to y coordinate means mathematically what we can write dy by dx is equal to y. Okay, dy by dx equal to y. Now what is dy by dx? Already we got dy by dx equal to 2x now. So in place of dy by dx, you can write 2x. That means 2x equal y. So we have to find the points which satisfies this condition, 2x equal to y. Okay, now what is y? Y is equal to x square. Okay, y is x square. Given equation, you see y is equal to x square. That means you got 2x equal to x square. Now we have to find the points which satisfies this condition. Okay, 2x equal to x square. 2x equal to x square. So I think you can find out now. 2x equal x square. So very easily you can calculate, you can find out the value of y. Let me see how many of you. Okay, some answer is coming. X equal to 2. Okay. Other responses? X equal to 2, x equal to 0, comma 2. Okay. 0, 0, comma 2, 4. 0, comma, okay, y equal to 0, comma 4. Okay. So responses are coming. So let us see what is the correct answer. Okay. Another comment, sir, can you please solve one case-based this question? Okay, I will do it. Okay, don't worry. X equal root 2. X equal root 2 is the okay. 2, 4. The point is given as 2, 4. So different responses are coming. Anyway, good. Some people have got only x equal to, you know, and some people have got the answer x equal to 0 and 2. So what is the correct answer? X equal to 0 and also 2. Okay, this is also one place where students used to commit mistake. That's why I have posted here. I want to see your answers. Okay, some people have done x and x cancelled, you know? Then directly you got 2 is equal to x, but that is not the correct mathematical way of solving. What we have to do is we have to bring everything in one side. Okay, 2x minus x square equals 0. Yeah, x square minus 2x equal to 0, which implies x into x minus 2 is equal to 0. This is the correct way of solving. Okay, x into x minus 2 equals 0. That means x equal to 0 or x equal to 2. So we have two values for x equal to 0 or x equal to 2. Okay, correspondingly, we will get y also. Okay, when x equal to 0, y also must be 0 only. And when x equal to 2, y will be 4 only. Okay, because the curve is y equal x square. Y is equal to x square. That means when x equal to 0, y equal to 0. When x equal to 2, y equal to 4. Therefore, therefore, the points are 0, comma 0 and 2, comma 4. 0, 0 and 2, 4. There are 2 points in that curve satisfying the given condition. Okay. 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 Now, I will do some more problems in the afternoon. Okay. Case-based study also I will do in the afternoon. So I have given some basic idea of the rate of change. Most of the problems are coming in this way. Now I will go on to the next topic. Definitely I will do some case study questions in the afternoon. Okay, I did not brought that questions now, that's why. So now we will move on to the next application, that is increasing, decreasing functions, increasing or decreasing functions. This is another important application of derivatives. Okay, we can use the derivatives to determine a function is increasing or decreasing. So before that, you must know what is meant by an increasing function, what is meant by a decreasing function. In increasing also there are two: strictly increasing, okay, and simply increasing only. Strictly decreasing, simply decreasing, okay. So the definition first you must be knowing, you must be thorough. Then we will know how to apply derivatives, how to apply differentiation in determining a function is increasing or decreasing. Okay. So please wait a minute. Okay. Just wait a minute. Okay. So in the screen you can see a graph actually. Okay. A straight line, you know, isn't it? A straight line actually. So this is an example. This is an example of a strictly increasing function. Okay. From the graph, you can observe that if I take some point here, okay. If I take some point -2, x equal to -2, okay, x equal to -2, the corresponding image, the corresponding value of the function will be here actually, no? -4. Okay. So when x equal to -2, the function value is -4. X equal to -2, the function value is -4. If I take x equal to some -1, x equal to -1, the function value is -2. Function value is -2. If I take x equal to 0, the function value is also 0. Okay. If I take x equal to 1, the function value is 2. If I take x equal to 2, the function value is 4. Okay. So it is going like this. No? So what we can observe, what we can observe, then when x is minus 2, function value is minus 4. When x is minus 1, function value is minus 2. When x is 1, function value is 2. When x is 2, the function value is 4. Okay, that means if the values of x are increasing, you know, when the values of x are increasing nature, increasing, the function value is also increasing. First it was minus 4, then it is minus 2, then 0, then 2, then 4. The function value is also increasing only. Okay, so this kind of functions is called a strictly increasing function. Okay, it is a strictly increasing function. So as x increases, the function value also increases. Then we say that the function is strictly increasing. That's the meaning of strictly increasing function. Okay. Now let me take another function. Okay. You see the second line, this blue line. So what we can observe? For example, if I take x equal to minus 2, the corresponding function value is 2 actually. When x is equal to minus 2, the function value is 2. Very clear. When x equal to minus 1, the function value is 1. Okay. You remember I am taking values for x in the increasing nature. Okay. X is increasing. If I take x equal to 0, function value is 0. If I take x equal to 1, the function value is negative 1. If I take x equal to 2, the function value is negative 2. Okay. If I take x equal to 3, the function value is negative 3. So what we can observe? As x increases, the function values are decreasing nature, decreasing. Okay. So this kind of function is called a strictly decreasing function. Okay. Strictly decreasing function. So that's the definition of the increasing and the decreasing function. Okay. Now we are going to study how the calculus, how the dy by dx, how the derivative can be applied to determine a function is increasing or decreasing. Always, it is not possible to plot the graph and see the nature. No? Practically, it is not possible. When a function is given, plotting the graph and seeing the nature mean that is not at all possible actually practically. Okay, so we need a technique. Using the derivatives, we can determine a function is increasing or decreasing. Okay, so these are the strictly increasing and strictly decreasing nature. Now, when we say only increasing, the graph may be in this way. Okay, increasing function means it will increase, strictly increase for some time, then it may be stable for some time, and again it will go on increasing. Okay, everywhere it is not strictly increasing actually. Okay, after some stage again it is some stable, it is becoming some stable, constant means no change at all actually. Then after some time again it is increasing. So if the graph is of this nature, then we say that it is only increasing function. Okay, there is no much difference actually, but this is the difference actually. Okay, there can be some part where the function is stable, no increase, no decrease, but totally the nature is increasing only. Okay, it never decreases actually. So this is called, if the graph is like this is called a increasing function, only increasing. Okay, similarly, what is mean by decreasing? So very easily you can guess, no? It may be strictly decreasing. After that, it may be stable, same, constant, no increase, no decrease. Then again, it will be decreasing. So if a function, the graph is like this, then we say that this is a decreasing function. Okay, this is a decreasing function. That is the meaning of the increasing and decreasing function. Okay, a strictly increasing and a strictly decreasing function. Okay, this is a fundamental basic thing only. Some functions we can easily say whether it's increasing or decreasing by seeing the nature also, using nature of the graph also. Okay, but always not it possible. So we need some calculus techniques, okay, derivative techniques, how to determine a function is strictly increasing or strictly decreasing. Okay, that we are going to discuss in this area, increasing and decreasing functions. Okay, let me take a okay. I think this graph is very familiar to you, isn't it? This is the function f of x equal to x square. F of x equal to x square. It's a very familiar graph, very familiar function for you. Many times we are using this, f of x equal to x square. So what you can observe from the graph, is it increasing? The domain of the function is all real numbers. Remember, okay, the domain of this function is all real numbers. Any polynomial function, the domain is all real numbers. In particular, x square. It's a polynomial function, so domain is all real numbers. So my question is, what can you say about the nature, increasing or decreasing? So from the graph. So if I take the negative portion, means negative real numbers, domain as negative real numbers, what we can observe, as x increases, the function from the graph, it is very clear the function is of decreasing nature. You know? The function is of decreasing nature, because if I take x equal to -2, the function value is 4. Okay. If I take x equal to -3, the function value will be somewhere at 9. Okay. The function value will be 9. So when x is -3, the function value is 9. When x is -2, the function value is 4. When x is -1, the function value is 1. When x is 0, the function value is 0. That means as x increases, the function values are decreasing up to 0 only. Okay, up to 0. Yeah, less than 0. Okay, less than the negative real number. If you take the negative real numbers as domain, in that interval, this function is of decreasing nature. Okay, and after that, if I take the positive real numbers as a domain, then we can see very easily, we can see that the graph is increasing. Yeah, the function is of increasing nature. You know? So here also the graph will help you to decide where it is increasing, where it is decreasing. Okay, so in this area, actually what we are doing is, some function may be given like this. Okay, so we have to determine the intervals. Okay, in which interval the function is of increasing nature, and in which interval the function is of decreasing nature. Okay, here if I take the whole domain or real as a real number, it is not neither increasing nor decreasing. We cannot say a complete nature in the whole real number. Okay, because negative branch means negative real numbers in domain, this is decreasing nature, this is of decreasing nature, and the positive real numbers, for domain of positive real numbers, it is of increasing nature. So throughout the real number, we say that it is neither increases nor decreases. Okay, it is neither increasing nor decreasing throughout the domain. But if I take only the interval from minus infinity to 0, minus infinity to 0, in that interval, very clearly, this function is decreasing. Okay, yeah, strictly decreasing. Up to 0, less than 0, it is strictly decreasing. 0, at 0, actually, there is a stable point actually. Okay, there is a turning point. At 0, it is becoming stable. And again, it is turning back actually. Now, for greater than 0, very clearly it is strictly increasing. Okay? Okay? So, from the graph, we can identify that in minus infinity to 0, it is strictly decreasing, and in 0 to infinity, it is strictly increasing from the graph. Okay? But again, we cannot draw the graph of all the functions, and we cannot identify the nature by drawing the graph or knowing the graph. So we need a technique. We need a derivative technique. So how can we determine a function is increasing or decreasing using calculus? Okay. So let me show you how this can be. In terms of slope, yeah, dy by dx. So wait. So what I have done is in the right side of 0, you can see a is a point on this function, and at that point I have drawn a tangent. Okay, a tangent is there, and you can see the slope of the tangent exactly. The value of the slope of the tangent at that point is 1.24, isn't it? Means right side of 0 in the positive side, positive domain. Now everywhere you see what is the value of the slope actually. Just greater than 0 also, the slope is now 0.48. Okay, 0.8. You know? So everywhere in this interval, the slope, you can see it is a positive value. You know? Slope is a positive number. That means dy by dx, the value of dy by dx is positive in this interval. Which interval? 0 to infinity. So that indicates the increasing nature of the function. Okay. So if a function is of increasing nature, then its derivative will be positive. Okay. If dy by dx is positive, we can say that that function is increasing. Okay. Now, if we come to the next negative side, means the negative minus infinity to 0 in that interval. Now you can see what about the slope of this tangent? Everywhere you can see the value is negative. Now it is minus 1.54. Okay. Minus 4.76. Okay. Everywhere it is negative only. Now also it is negative only. Less than 0. Okay. Negatives domain, the value of the slope is negative. Everywhere it is negative. Okay. You can see everywhere the slope is negative only. That means when the slope is negative, the function is of decreasing nature. Okay, the function is of decreasing nature. When it reaches this point, means when we exactly reach at 0, the slope will be 0 actually. Okay, after closing again it will be positive. So clear? So this is the idea what we are using to determine a function is increasing or decreasing. Okay, and at the point 0, very clearly the derivative must be 0 also. Okay, if I adjust this point to coincide exactly at the origin, you will get 0. Okay, now you can see at the point 0, m is 0. M means slope actually. Okay, at that point 0, the tangent itself is the x-axis and the slope is 0 only. So if there is a turning point, okay, if there is some turning in the graph, at that point the derivative must be 0. Okay, and easily we can identify whether the slope is positive or negative. If you calculate the derivative, dy by dx, you can easily find whether the value is positive or negative. And where it is positive means the function is increasing, and where it is negative means the function is decreasing. Okay, so that is what we are going to do in this section. Okay, some problem will be given, some polynomial, some function will be given. The question will be identify the interval. Yeah, find the intervals in which the function is increasing, yeah, function is decreasing. Okay. Now, if I do algebraically, The same problem, how can we f of x? The function is f of x. We don't know graph or anything. We don't know anything. So we have to identify the intervals where this function is increasing or where this function is decreasing. Okay. So what we have to do is just to find the derivative. F dash x, everybody can find the derivative. So f dash x is 2x. Now we will see where this function the derivative becomes zero. If there is a increasing change, increasing and decreasing nature, okay, then definitely there must be a turning point. Okay, at that turning point, the derivative must be zero. So if I equate f dash x equals zero, what happens? 2x equals 0, and we will get x equal to 0. Okay, that means at x equals 0, the derivative is 0. Okay, so that indicates that at that point 0, there is a turning. Some turning is happening at the point 0. Okay, so 0 is the turning point for that function actually. So after getting that turning point where the derivative is 0, let us mark in the domain. Domain is all real numbers. Okay, roughly we can draw a number line and mark 0. Okay, 0 is the turning point actually. Okay, so that means left side of 0 and right side of 0, the derivative may be positive or negative. We don't know where it is positive or it is negative. We don't know actually. Okay, we don't know anything about the graph. So now I am going to check in this interval, the first less than 0. You know, there are two intervals actually. There are two intervals. Okay, first one is minus infinity to 0, minus infinity to 0, and second one is 0 to infinity. Clear? 0 break the interval, the domain into two parts. Okay, minus infinity to 0 and 0 to infinity. Now you take the one of the interval in minus infinity to 0. What I have to do is I have to check the sign of the derivative. That's all. Okay, sign of the derivative. What we have seen observed in the graph now, when the derivative is positive, the function is increasing. When the derivative is negative, function is decreasing. Okay, so in the interval 0 minus infinity to 0, let me check the sign of the derivative. Only the sign is enough for us. Okay, sign. So what is derivative actually? 2x. You know? So in this interval, if I find the value of 2x, what will be the sign of 2x? For that, what we do? You can take any value from that interval. Okay, you can take any value from that interval, any number from this interval, any number, -1, -2, -3, whatever. And you substitute in that derivative. Derivative is 2x. So if I put a -1 belongs to this interval. So I will get a 2 into -1. Okay, you can check in your mind. Okay, so 2 into -1 means -2. That means it is negative. Okay, or if you take a -2 also, 2 into -2 means negative, 2 into -3 means negative. Everywhere it will be negative only. So the function derivative is negative in the interval minus infinity to 0. That means the function is of decreasing nature. You know what we have observed in the graph also. This is the algebraic method. Okay, I am telling the algebraic method. Now let us take the other part. 0 to infinity. You take any point in between 0 and infinity. Okay, you can take 1, you can take 2, all belongs to that interval. And check again. What is the sign of the derivative? Derivative is 2x. Okay, f dash x is 2x. So if I put x equal 1, 2 into 1 positive. If I take x equal 2, 2 into 2 positive. Clear? That means in that interval, f dash x is positive. Okay, 0 to infinity, the derivative sign is positive. If you want, we can make a table also in a neat and clean way. Also, we can write while writing the answer. Okay, like this. You list the intervals and you find the sign of this f dash x in each of the interval. So minus infinity to 0, the derivative is negative. 0 to infinity, derivative is positive. That means minus infinity to 0, the function is strictly decreasing. And 0 to infinity, the function is strictly increasing. Okay. Okay, now the time is already 8:30. So I think we have to wind up here. We will continue with the other concept of this chapter and more problems in the afternoon and evening session. Okay. And any query is there, you can put in the chat box. Okay. We will see it, and the common issue that we will be addressing. Okay. If you have any doubt, any query, you can just type in the chat box. Some comment is there, I will see. Uh, just a minute. I am Rudresh for the given curve y is equal to 5x minus 2x cube when x increases at the rate of 2 units per second, then how fast is the slope of the curve changes? Okay. Okay, your responses will be already stored here. I will be seeing it, okay, later. Okay. Show that the function tan x minus 4x is strictly increasing. Okay. Show that the function f of x equal to tan x minus 4x is strictly increasing in pi by 3 to minus pi by 3 to pi by 3. Okay. I think that problem is already with me. I am going to discuss that problem. I think that problem is already in my list actually. Some problems I have selected that, okay, tan x minus 4x is strictly decreasing on minus pi by 3 to plus pi by 3. Okay, that I will be discussing in the afternoon. Okay, don't worry. Okay, then we'll stop here. Okay.